Okay, this is a video where I'm going to go through all of the AES and A-level differentiation. Right, so let's start with the notation that we use. Now, if you start with y, then you should write dy dx, that's the Leibniz notation. If you have f of x, then when we differentiate, we should write f dash of x, which is Lagrange's notation. And particularly for mechanics, if we have x as displacement, then we can write dx dt, the velocity, with x as a single dot over the top to indicate that we differentiated once, and this is Newton's notation. Next, we'll look at doing differentiation from first principles. So here we have the first principles formula here. We're finding the limit as h tends to 0 of, basically it's like the change in y over the change in x. We also need to be able to prove the results for differentiating sine and cos from first principles, and when we do those, we use the small angle approximations for those proofs. Now the small angle approximation is in radians, so the proof for sine and cos is in radians. So whenever we use sine and cos and we're differentiating or integrating, doing any calculus, actually with any trigonometry, then it must be in radians. Next, we're going to look at some standard results. So these are the results that you would be expected to know off by heart. So we have a polynomial where you multiply by the power and subtract 1 from the power. E to the x doesn't change when you differentiate it. Log x becomes 1 over x. Sine x or sine theta becomes cos x or cos theta, and cos theta differentiated becomes minus sine theta or minus sine x. And a to the x, so a constant to the power x, becomes a to the x log a. Now, as I've just mentioned, these ones with sine and cos here, the angle theta or x or whatever variable you have here needs to be in radians. Next, we're going to be looking at the chain rule, and the chain rule we use when we want to differentiate a function of a function. Okay, so the two steps are that we differentiate what I call the outside. So imagine the function of a function, there's somewhere where you can put brackets, whatever's outside of the brackets I call the outside. We want to differentiate that, and then we multiply by the inside, whatever we put inside the brackets, differentiated. Now it's important to note that whatever's inside the brackets doesn't change. So I'll do an example. So let's say we had y is equal to sine of 3x squared minus 2x, so I can clearly see that my outside is sine, the inside is this 3x squared minus 2x. Then dy dx, differentiating the outside, sine becomes cos, that's one of the ones in my list here, so cos. The inside doesn't change, so it's still 3x squared minus 2x, and then I need to multiply the whole thing by the inside differentiated, so that's going to be 6x minus 2. So there we go. That's using the chain rule to differentiate this function of a function. Now you'll also come across the chain rule when you are trying to solve differential equations, and let's say we have a question where we have or we want to work out what dA dt is, and in the question we've managed to work out what dV dA is, and we've also worked out what dV dt is. So you can think of these like fractions, multiplying them together. So to get dA dt, I would need to do, and before I do that, I just need to change this t to an a. I would need to do the reciprocal of the first fraction, so dA dV, and times that by dV dt, and you can see what will happen is that the dV's will cancel out, leaving me with dA dt. So this is also the chain rule as well. Now the chain rule also gives us some quick ways of differentiating e to a power other than x, so e to a function power, and that could be anything. And using the chain rule, what that will become is f dash of x times by e to the f of x. So basically you differentiate the power and multiply by that differentiated power. And we've also got a nice quick rule that we can use for differentiating the log of anything other than x, the log of a function, and that will end up as f dash of x over f of x. So whatever you're doing a log of, that thing goes at the bottom, and then that thing differentiated goes at the top, and then you may need to simplify your answer after you've worked this out. Next is the product rule, where we have a product which I'm going to call u and v, and then dy dx will be equal to u v dash, so the v part differentiated, plus v u dash. Now because this is an addition, you can do this in either order, it doesn't matter which way around you do it. Next we'll look at the quotient rule, and with the quotient rule we're going to have a function which is something divided by something else. I use u and v again, and then dy dx is going to equal to, now the order of this is important because we're going to have a subtraction, so it's v u dash, we start at the bottom and then times by the top differentiated, minus, then we start with the top and times it by the bottom differentiated, all divided by the bottom squared. Now the quotient rule is actually like a pair of trousers, because the quotient rule starts at the bottom, v, and finishes at the bottom, v. My little joke there. So here's a pair of trousers for you to remind you about how the quotient rule works. Next thing we're going to look at is implicit differentiation. Now with implicit differentiation, what we're going to have is a function of x and y. Now what we don't try and do is to make y the subject, because you'd end up with all sorts of messy things, but there are some steps we need to take. So what we do is we differentiate any x terms in the function as normal. We differentiate any y terms as if they were x terms, but then we need to add dy dx to show that we've differentiated a y term as if it was an x, and then we use the product rule for any x, y terms. So here's an example. So the x term we just differentiate as normal, so that becomes 8x. Then the 7y we differentiate as if it were an x, so that's going to become minus 7, but we add the dy dx to indicate that's what we've done, differentiated a y term as if it was an x. Now for this part here we need to use the product rule. So if I start with the 3x, let me just highlight it. So think of one part as my u and this part here as my v, and we've got the product rule over here, so we're just going to apply it. So starting with u, then I will have just plus 3 x, so I haven't differentiated that. Then I differentiate the y squared. Now that will become 2y, and then I added dy dx because I've differentiated that y term as if it were x. Then the other part of the product rule means that I need to differentiate the u part. The 3x will become 3, so plus 3. The y squared stays the same because that's like the v part, and that's going to equal to 0 because we differentiate the 12 as well, so that just becomes 0. And then what we can do from here is, if we needed to, we could rearrange it and then make dy dx the subject. Next we'll look at parametric differentiation. Now with parametric differentiation, this is where the x term is a function of t, and the y term is going to be a different function of t. And in a question like this we would need to find dy dx, and dy dx is going to be dy dt divided by dx dt. So in terms of the function notation that I've used, that will be g dash of t over f dash of t. So the x part differentiated, sorry, the y part differentiated over the x part differentiated. Here, if I wanted to find what the gradient was, I would need to substitute in the appropriate value of t. Next, we're going to look at uses for higher derivatives. That's the second and third derivative of a function. Now, we know that when dy dx is equal to 0, we have a stationary point. We often need to be able to classify and work out what type of stationary point we've got. So that's where we turn to the second derivative. We substitute in the same value of x that we've plugged into dy dx. If we get a value of the second derivative which is greater than 0, we get what's called a local minimum. That just means it's a minimum in that area of the graph. You can just use the word minimum. If the value of the second derivative is less than 0, we get a local maximum. It just means it's a maximum in that area of the graph. Notice the signs are the opposite to what you would think. Greater than 0 minimum, less than 0 maximum. Now if the second derivative works out to be 0 when we substitute in the value of x, there's no way of telling what type of stationary point we have. So this is where we turn to the third derivative. And if the value of the third derivative, again with the same value of x substituted in, if this is not equal to 0, then it tells us that we have a point of inflection. Now, last thing is that we can also use the second derivative to classify parts of a graph as being convex or concave. So when the second derivative is greater than or equal to 0, the graph is convex. Now, one way to recognize whether a graph is convex is because all the tangents that you would draw on that graph would be above the curve rather than below the curve. I haven't really got any space to show you that, but imagine that you've got a curve, you draw tangents, all those tangents are above the curve, then it would be convex. If the second derivative for a range of values of x is less than or equal to 0, then the graph is concave. That means if you were to draw any tangents to the graph, they would always all be below the graph. So again, haven't got space for that, but maybe think of a particular graph that if you were to draw the tangents, all the tangents are below. So in that range of values, the graph would be concave. And if dy or the second derivative changes sign from either being positive to negative or negative to positive, the graph is neither convex or concave. What we have is a point of inflection.